Hello class, this is our first lesson. It's going to be the overall topic of relations and functions, and so it's going to be section 1.1, and we're going to examine sets of numbers. So these are going to be the different objectives that we're going to be looking at. Our first objective says that you guys will be able to describe a set in 3 different ways. You're going to be able to classify the different sets of numbers, and then we're also going to write a set of real numbers in interval notation. So the first we need to do is define what a set is. Now it says that a set is a well-defined collection of objects which are called elements of the set. So everything inside of our set, we just call it an element. Now well-defined implies that it is possible to determine if something belongs to the collection or not without any form of ambiguity. So it's either it's part of it or it's not part of it. There's no, well, maybe it's part of it, it is or it isn't, yes or no. So an example here, it says the collection of letters that make up the word materia is well defined as is a set, but the collection of the worst math teachers in the world is not well defined, and so is not a set. And the reason is because there's an ambiguity in the sense of what makes the worst math teachers in the world. Some people might say it's this, some people might say it's that. I mean, you know, there's no well-defined features. But here, the well-defined feature is the collection of letters. Well, the letter M is either in the set or it's not in the set. In this case, it is. Is Z part of that set? No. And so it's easy for us to be able to say that this is defined or if it's not defined. Now there's going to be 3 ways that we can describe a set. The first is the verbal method, and that's just using any old sentence to define whatever that set is. The second is going to be the roster method, and we're going to use this bracket notation, and generally it's going to start with a left bracket, and then we're going to list each element of that set only once, and then it's going to end with a right bracket. And then the third method is called the set builder method, and it's going to have a combination of the verbal and roster method, and it's going to use a variable to kind of associate with that given set. So let's examine the different ways of doing this. Let's say I have set S, and we're going to describe it verbally as the set of letters that make up the word smoko. So a roster description of the S would be the letters S, M, O, L, K. Notice that even though I have O twice in here, I only listed O once. And so it doesn't matter which way that I would actually write it. And so the verbal is actually, like I said, going to be just listing those words. And then the set builder method is I'm going to say X, so I'm defining my variable, X, and then X is going to be the letter in the word smoko. So I define it, that's my quote-unquote dummy variable, and I'm going to say that X is going to be the letter in the word smoko. So if you notice, it was kind of like the combination of this and this put together. Now, when we're examining sets, we're going to look at the different sets of numbers, and these are essentially all those different sets of numbers, and you're going to find that some of these numbers are going to be embedded in other numbers. So the empty set is the set with no elements. There's nothing in it. Like the number 0, it's going to play a vital role in math. The natural numbers, okay, we call these also like counting numbers. These are going to be defined as set n, and it's basically positive whole numbers. All the whole numbers include 0, so 0, 1, 2, 3. Then integers, we say that it's this special looking z. Those are going to be positive and negative whole numbers. Rational numbers, we define that as set q, is going to be all the different combinations of one number over another. And we basically can create a ratio from this. Now notice how these sets build off of each other. Natural numbers are within whole numbers. but whole numbers are not within natural numbers because we don't have the letter 0. These natural numbers and whole numbers are in the set of integers because we have these numbers and these numbers inside here. But a -3 is not in W or in N, so I can't say that -3 is within those. And so we're actually able to say that some of these sets kind of build off of each other. Like rational numbers, the number 1/2, that's a rational number. It's a ratio. But this rational number is not an integer. But I can say that 3/1, which is a ratio, that's an integer. So just understand that some of these sets are embedded within each other. Real numbers is any, it says x possesses a decimal representation. So 3, 3.2, 3.876 with a little dash over it. However you want to represent it, it's just any real decimal representation. Rational numbers are real numbers, integers are real numbers, whole numbers are real numbers, natural numbers are real numbers. Those are all whole numbers. Irrational numbers is any number that I'm not able to make it into a ratio. So the idea of having 0.33 with this bar. I can say that that's approximately 1/3, but 0.33 going on forever, it's impossible for us to make it into a ratio. You know, pi. Pi is also an irrational number because it goes on forever. There's no possible way for me to make it into a ratio, and so therefore it's going to be an irrational number. Now, irrational numbers are real numbers, but irrational numbers are not rational numbers. So they're like completely separate sets. And then the last is going to be a complex number. Now it's any number that has this imaginary component I with it. And so we know that I is going to be the square root of -1. And so we're going to be examining these complex numbers later on in the text and later on in this class. But just understand that it's kind of like almost like a separate segment. Complex numbers have its own special set, and we're going to define that as set C. So notice all of these sets of numbers have a special number, or I'm sorry, letter that we kind of defined to it. I could be using these letters later on in class, and you kind of have to realize, wow, if I'm using W, I'm referring to the set of all the whole numbers. If I use Z, it's the set of all integers, which means positive and negative whole numbers. And so this is going to be something that you guys are going to have to recognize. Now, when we look at these numbers, for the most part, we're going to be examining real numbers. Now, because we're examining these real numbers, we kind of got to think of this, okay, real numbers, we can express them on a number line, right? So we can look at this number line, and we know it's like 1, 2, 3, and this is -1, -2. We can say this is right here, this is -1.5. You know, we can express all of these numbers on a number line. Now, because of that, we could draw segments of these number lines to kind of define where this certain region exists. And that's usually a common application for it. And so there's actually different ways for us to be able to write these sets in terms of intervals. And so what I have here is I have a comparison chart that allows us to be able to translate what I wrote as a set notation into a real a region on a number line. Okay, so typically if we have a set, it's easier to write and recognize as an interval and then express it as a region on that number line. Now there's a few things we need to qualify first. First of all, whenever we have brackets or parentheses, brackets is referring to a closed dot, parentheses is referring to an open dot or infinity. Negative infinity, we're generally going to draw an arrow that goes this way forever. Positive infinity, we're going to draw an arrow that goes that way forever. So when there's equal to closed dot, that means that the value is included. We are allowed to include that value in our solution or in our region. And so that's why we're going to use brackets. I guess maybe another way of thinking about it is less than or equal to, right? If you see things like that, we know that it's going to be open dot or parentheses. So now translating this, what this is saying is our variable x, where x is between the values a and b, not inclusive, meaning I'm not including a and I'm not including b in my solution. So x is between a and b, which means that this value a is going to have a parenthesis because there's no equal to. This value b is going to have a parenthesis because it's not equal to. And so now drawing this from a to b, not including a, so not including a, open circle, all the way to b, not including b. And so basically all this is just the different representations of how I want to look at these sets and translate them into real numbers. This one is saying here x is between a and b, where a is included and b is included. So everything between a and b, the brackets mean it's inclusive. And so that's why I have a closed circle here for a and a closed circle here for b, is because I'm also including a and b in my sketch. When I'm saying like x is less than or equal to b, what I'm saying is that every value for x is going to be smaller than b. So that means that, thinking about it, it's going to be from negative infinity all the way to b because of that equal to sign. That's why b is inclusive here. And so it's going to be everything less than b all the way to that b inclusive. Now if we have any questions on this portion, please leave comments in the video. More than happy to address those. But just understand that this is kind of like an overall, I'm not going to spend a whole lot of time on this, but this helps us translate what those are going to be. So to apply a real example to this, let's just say if I had x where I have the numbers between 1 is less than or equal to x, which is less than 3. Okay, well if I wanted to translate this over, x is between 1 and 3, so I know it's going to be between 1 and 3, so that's why I have the numbers 1 and 3. Right here it's going to be a bracket, because it's an equal to, so bracket. Because there's no equal to here, that's why it's a parenthesis. And so since it's saying x is between 1 and 3, well, I can draw a segment between 1 and 3, closed circle, open circle. X is between -1 and +4. Closed circle, so between -1 and 4, closed circle and closed circle. If I wanted to express that as interval, I would say from -1 to 4, there's going to be brackets around that. X is less than or equal to 5, so that's going to be -infinity to 5. That's why I have that arrow going on forever, so all the way from -infinity, and it's going to stop at 5. Now we're going to talk about how sets can intersect each other, or how we can combine sets together. Now if you had noticed, when I was talking about whole numbers and integers and rational numbers, I made mention that sets, you can find sets that exist in other sets. Well, here with an intersection, what we're saying is that the intersection of these is saying if we have two separate sets, what's going to be in both of those sets. So that's going to be where my element of x is in A and it's in B. And we use this upside down symbol, or we're going to, we just use this upside down symbol. It's kind of like this, I don't know, it's not an N. We don't want to say it's an N, but this little symbol literally means the intersection of, and it's only what exists in between both of them. Okay, and sometimes you're going to see this phrasing and when it comes to that. Now the union of A and B, we use this U shape, and what this is saying is the elements in A or the elements in B, which implies it could be from both of them as well. So you also include what exists. Now a visual representation of these, let's take a look at the intersection. So if I say that this circle represents all the elements of A and this circle represents all the elements of B, the intersection of those is just going to be what's in both of them. And so that's going to be this region here. The union, we said that it's the elements of A or the elements in B or both of them. So everything's going to be shaded. It's going to be everything in A and it's going to be everything in B. Now let's kind of look at like a brief example of what I mean here. Let's just say if I said A is the numbers 1, 2, and 3, and B is the elements 2, 3, and 4. If I wanted to find the intersection, I'm looking at what exists in both of them. Well, only 2 and 3 exists in both of them. And so my answer, and when I'd say what's the intersection of those two, I'd say it's 2 and 3. Now the union of both of these, A, U, B, that's going to be everything from both of them. So the numbers 1, 2, 3, and 2, 3, and 4. So I have 1, 2, 3, and 4. Now notice I didn't do any repeats because in the very beginning when we defined the sets, we said when we're expressing it like this, we're not going to have any repeats. You don't need to, okay? You don't need the repeats. So let's examine a few examples here. It says express the following sets of numbers using interval notation. And so for this one here, it says x is less than or equal to -2, or x is going to be greater than 2. So it kind of helps us first when we're imagining what does this look like on the number line, right? Because our goal is we want to write it in interval notation, and so imagining what it looks like on a number line makes it so much easier. Expressing this on a number line, first one it says x is less than or equal to -2. So let's draw our number line, and we know that here's -2. Because there's that equal to, I know that this is going to have a whole circle here. It's going to be solid there. And it says x is less than or equal to -2. So that's going to be everything that's less than that. And it says or x is greater than or equal to 2. So that means I also have this 2, and everything's greater than that. And so now that I have this visual representation, it's going to be much easier for me to be able to look at that and be able to draw it. And so imagining this starts from -infinity. So from -infinity, it's going to go to -2. So I'm going to say from -infinity, it's going to go to -2, union, and then it's going to go from 2, right? Because there's nothing here. There's nothing here, but I have two sets. And so we said that phrase union means I have to combine these together. So I have this from -infinity all the way to -2, closed circle, that's why I have a bracket, nothing here, so it skips it, and then it starts here again at 2, so 2, and then it looks like it goes on to +infinity. And so that's going to be the interval notation for being able to create that from the set. So just remember, the first thing that I did here is I kind of drew it out, because it helps, and then I was able to create the interval notation from that. Let's examine another one. It says x, where x cannot equal 3. So let's draw out that number line. We said that x can't be 3. So let's say that this is 3 here. We're going to put an open circle there, because we said it can't be that. But it never gave us any other restriction, so I'm going to make the assumption that x is everything else. Because right now, that visual representation is saying it's everything else but that 3. So now trying to create that interval notation, it starts all the way from over here, so that's -infinity, and it's going to keep going until it gets to 3. So I'm going to say -infinity all the way to 3. Now I have more, so union. Now notice I did a parenthesis here because at that 3 it's open circle. Now it's going to kind of start at 3 again, and then it's going to go over to infinity. And so I'm going to say parenthesis, since it's open circle, 3 all the way to +infinity. And that's going to be my answer. Now I want you guys to give this one a shot, and then we're going to check it. So go ahead and pause it and try and solve it, and then we'll check the answer in a moment. So checking the answer here, it says x cannot be plus or minus 3. So drawing it out, we said it can't be plus or minus 3, so I guess those are my key numbers here. It can't be -3, and it can't be +3. But there's no other restriction, so I can assume that it can be everywhere else. And so now in step 2, it says create the interval notation from the number line. So now we just need to translate this. So it starts at negative infinity and it goes all the way to negative 3. So from negative infinity goes all the way to negative 3. Now there's more, so union. Then it's going to be from negative 3 all the way to positive 3. So I'm going to say negative 3 all the way to positive 3. Now there's more, so union. And then it looks like from 3 all the way on, so 3 all the way to positive infinity. And so that's going to be my answer. Again, let's take a look at this. I want you guys to give this one a shot, and then we will go over it. So checking our work here, it says that x has to exist between negative 1 and 3, or x has to be 5. Okay, so it's one of those. So let's kind of draw that out. So we're saying x is between negative 1 and positive 3. Now, those are going to be open circle because they're not equal to, right? There's no lines here, so that's going to be open circle. But x is between that, so I can shade that. And then it says x is 5. So at 5, I can put a nice little closed circle here. So now drawing this, I'm going to say that there's nothing over here. Okay, there's nothing here, so there's no negative infinity. It doesn't start until I get to negative 1. So at negative 1, it's going to go all the way to 3. And I use parentheses because these are open circle. Then there's a gap until it gets to 5. And so I'm going to say union 5. Now I did brackets because it's including that value. There's nothing else, and so that's going to be my answer. Now as we conclude our lesson, every single closure or conclusion, basically I'm going to have a set of questions like these. So what did we learn today? Well, we learned a few things like describing a set of in 3 different ways, classified the different sets of numbers. We write a set of real numbers in the different interval notations. Now, what did you learn? Right? Are those the same thing? Are there anything extra that maybe you didn't realize necessarily in math class and you're like, oh, that is kind of interesting. I never really thought of it that way. What I want you guys to do is I want you guys to go ahead and leave a comment under the video. So it's YouTube, and so you can leave comments. I want you to leave your response of what is it that you learned today. Now, I also, in reflection, I want you guys to answer the other 2 questions. What were the 3 different methods to build a set, and what is the difference between an intersection and a union? These are going to be talking points that we could discuss in class tomorrow. Now, if you do have any questions with the lesson, you're going to see this same type of response. Go ahead and leave it in the comments. Maybe there's an Easter egg. Maybe I deliberately left something incorrect and I kind of want you to find it. These types of things are opportunities for extra credit. So look for them. If I made an error, if it's a typo, that's unintentional. But sometimes I'll forget a negative somewhere, or I'll multiply when I really need to divide. Just little things like that I'm hoping that you guys would catch on to see if you guys can find those errors, kind of like create that active participation. So I want to hear from you. So like I said, if there's anything else that you learned today, I want to hear from it. And then go ahead and answer the other 2 remaining questions. What were the 3 different methods to build a set, and what is the difference between an intersection and a union? And if you do have any other questions, please leave them in the comments.